Alright, class. Hope you had a good spring break. Today we're going to learn about mixing problems. Well, what are mixing problems? So, it's a typical application of separable differential equations. So just like when we learned about derivatives, like a typical derivative problem might be related rates or optimization. So once we now know separable differential equations, we're going to use them to solve mixing problems. Alright, so what does a mixing problem look like? Well, here's my beautiful picture right here. So imagine you've got some sort of tub or basin filled with liquid. And the key thing to a mixing problem is that you've got something coming in, and it's mixing in instantaneously with the stuff that's in the basin, and at the same time it's pouring out. And the question is, how is the concentration in this original basin changing based on the concentration coming in and the outflow over here? So it doesn't necessarily have to be a liquid, but just for this very first example, this kind of simplistic case, I like to imagine it being paint. So imagine you've got some mixture of black and white paint in here. So I'm going to say it's like the concentration of gray. So if it actually has a 100% concentration, that means it's completely black. If it's 0% gray, that means it's completely white. So let's start off and just say that our original tub right here holds 500 gallons, and it's at a level of 80% gray. So you can think of it as being like 80% black, 20% white. So this is the grayness level right here. So pretty dark. On the other hand, there's something pouring in, so a kind of lighter color pouring in. So I'm going to say it's a 30% concentration, so 30% gray color, which is coming in. And it's important to know not just the grayness level of the incoming, but also how fast it's coming in. So I'm going to say that it's pouring in at 10 gallons per minute. So we start with 500 gallons, that's pretty dark, 80% gray, and in pouring in as a fairly light mixture, it's coming in at 10 gallons a minute, it's only 30% gray. Now, if that's all that was going on, then the amount in the bucket would eventually overflow, because first I have 500 gallons, and 510, and 520, 530, but I want to keep the amount in the bucket even. So now later on you'll learn how to deal with if it's not even, if the amount is growing or shrinking, but in a first level calculus class we're just going to keep the level even. So we're going to have a little spigot out here where the paint is pouring out. So I'm going to say that the outflow is going at 10 gallons per minute. So I had it be exactly the same as the incoming, so that way the amount stays balanced. Now it's also important to make this kind of simplifying assumption that as soon as it pours in, it mixes instantly. So in reality, if the spigot was sort of at the bottom of the bucket, that at first when it poured in, you would just be getting the 80% gray out until it like slowly mixed in. But that involves more complicated equations. So we're just going to assume that as soon as it hits, it instantly mixes in. So now if you just sort of think about it intuitively, what's going to happen is it's going to start out 80% gray. So that first split second when it comes out, it's coming out pretty dark. But then as time goes on, as you get this sort of 30% mixture coming in, this is going to get more and more like the 30%. So it'll never be completely 30%, because there'll always be that little bit of darkness that's still left. But it'll get closer and closer to the 30%. So, alright, so the question that we're going to ask is, how long until the mixture in the bucket is at 40% gray? So right now it starts out at 80%. We're mixing in 30% continuously, and it's also pouring out at 10 gallons per minute, so it keeps the bucket even. How long until it hits 40% gray? That's the question that we want to answer. Alright, so how are we going to solve this? So first let me just put in the corner all the pertinent information that we had. So we started with a tank of 500 gallons with 80% gray, and the pipe going out is 10 gallons per minute. The pipe going in is also 10 gallons per minute of 30% gray solution. So let's make a function for the amount of blackness that's in our tub. Now that changes over time, so it's going to be a function. So let capital A represent the amount of black paint in the tub in gallons at time t, where t is measured in minutes. So we want to come up, our goal is to come up with a formula, an explicit formula for A of t. So a formula of t's. So, well, what do we know about A? Well, the only thing we really seem to know at the outset is that when we started, before we turned on any of the pipes, there was 500 gallons of the tub of 80% gray. So that how much black would have had to have been there at the very start? Well, a of 0 at time 0 would be 500 times 80%. So 80% of 500, 500 times 80 is 400. So we know that a of 0 is 400. But that just gives us one single point. We also need an entire formula. That's going to end up being our initial condition, which we're going to use to solve for the c when we get the differential equation. But how are we going to figure out this differential equation? What is the derivative? So this takes a little bit of thinking, but let's look at the change in the amount of black. So let's look at the derivative. dA dt is equal to the change going in minus the change going out. So let's just think about this for a minute. If I say that, remember, A represents the amount of black. So if I say, hey, at some particular moment, there's 7 gallons of black coming in, but there's 3 gallons of black coming out, I'm just making it up, that would mean that the total change in blackness at that split second would be 4, because there's 7 blacks going in and 3 blacks going out, so dA dt would be 4. So it's always going to be change in minus change out. Well, what is the change of blacks coming in? Or how much black is coming in every single minute? Well, if we just come up here, we know that there's 10 gallons per minute going in, but not all of it is black, because we're only putting in a 30% grayness level, right? So therefore, the actual amount of black going in is not all of the 10, it's 10 times 0.30. That's the 30%. So that's how much black is going in every single minute. Well, how much is going out? So, well, we know there's 10 flowing out, so it's going to be 10 times, 10 times something. But it's not 30%, right? The 30% is what's going in, but what's coming out is whatever was in the original, not the original, but in the tub. And a lot of people want to put 80% here. But it's not 80%. It's only 80% in that very first split second, back when it was the original gray color. But that gray color is getting diluted. Every single moment that's going by, that 80% is getting less and less and less. So we have to figure out what is the concentration, what is the grayness level in the tub. Well, the way you figure out the grayness level is you take the amount of black divided by the total amount, right? So for example, if we had, 500 gallons and 100 of it was black, then our concentration level would be 100 over 500, right? So it would be 20%. So in general, it's the amount of black divided by the total amount of paint, which is always going to be 500 because of the fact the inflow and the outflow is the same. It's always 10. 10 going in, 10 going out. So the total amount in the tank is always 500, and the amount of blackness of the tank is what we're designating as A. That's what we said A was. A is the amount of blackness. So our concentration is A over 500. That's our percentage. And we're multiplying by 10 because that's the outflow amount. So all of this is the change in blackness going out. The 10 times 0.30 was the change going in, and we're subtracting them to get the total change. So that's what dA dt is. Well, let's just do a little bit of algebra simplification on this. So that means dA dt is equal to, so 10 times 0.30 is 3, and here I'm just going to cancel the 10 to the 500, write it as A over 50. But we can do some more algebra simplifying on that. So let's make a common denominator. So this has a 50, so let's make that be 50. So that would be 150 over 50. That's the 3. And let's put this now over a common denominator, so as a single fraction. So that's 150 minus A all over 50. And now look at this. This is a separable differential equation, which is exactly what we learned how to solve before spring break. So let's go ahead. We need to put all the A's on one side and all the T's on the other side. Of course, there are no T's, so that makes it kind of simple. So we have to divide this out on the other side and multiply the dt over. So what we get is the integral of dA over 150 minus A is equal to the integral of dt over 50. And now what you have to do is do calculus to figure out what that is. Alright, so let's focus on solving this differential equation right here. So let me put it up in the corner. And the first thing to do is let's handle the left-hand side here. And we can see there's just a little bit of wishing game. We can make this look like natural log. So we think to ourselves, alright, the derivative of the bottom, derivative of 150 minus A, would just be negative 1. So we just kind of wish that, hey, if there was a negative sign on the top and the bottom there, so I'll just pull that negative sign out, then it would work out perfectly. So we still have this negative sign on the outside of the integral, and the inside just becomes the natural log of the absolute value of the bottom, which is 150 minus A. And then that's equal to, well, here this is just the integral of 1/50th dt, so it's just t over 50. Now don't forget, there's a plus c over here. These are indefinite integrals. Technically, there'd be a plus c on this side. We move it over and it would get absorbed. We just write a single plus c on the side. Now we want to get rid of this natural log here. Now the usual way to get rid of natural logs is by using this as an exponent on an e. But we can't do that right now because there's a minus sign in the way. So we need to get rid of this minus sign. So I'll just move the minus sign over, multiply everything by -1. So that'll get rid of the minus sign here. It'll put a minus sign here. Technically also a minus sign on the c, but the c is just going to eat it. So it's going to stay a plus right here. Really, it'd be minus c, but again, it's a cannibal, so it eats the constants. So now that we got the natural log all by itself, now we can raise it to the e power. Do that to both sides. So on this side, the e and the natural log are just going to cancel, and you're going to be left with the absolute value of 150 minus a, and that's equal to e to this times e to the c. So you have e to the negative 250 times e to the c, but again, as usual, the constant here, c, is going to eat the e, just become a general c, which I'm just going to go ahead and write in front. And then we also want to get rid of these absolute values. So if the absolute value of something is equal to a constant, that means the thing inside must be plus or minus that constant. So we get rid of the absolute values simply by writing a plus or minus in front. But hey, that c is going to eat that plus or minus, so we can just ignore that plus or minus. And last but not least, we want to solve for a. So we can just swap positions of the a here and the c e to the negative 250 here. E to the negative t over 50 here. So I change places of those, like so. But again, we've got a negative in front of this c, so we'll just go ahead and eat that. So make it be a plus. Just looks a little nicer. All right, so we basically have it. We've got a equal a formula of t's. The only thing is we've got this constant of integration right here. We've got this c. So, but don't forget our initial condition. So our initial condition was that a of 0 is 400. So if we just plug in t to be 0 here and a to be 400, we solve for c, just like we normally do. So, well, 0 divided by 50 is 0, negative 0 is just 0, e to the 0 is just 1. So this really just goes away. So what you have is 150 plus c equals 400, so you scoot the 150 over, and we finally have that c is equal to 250. Now, that's just what c is. We still need to figure out what our original equation is. So we go back up here, but instead of writing c, we're going to write 250. So a is equal to 150 plus, but instead of c, we say 250 e to the negative t over 50. So this right here is our particular solution for the amount of blackness in our tub. But we still have not answered the question. But to this, let's actually look at a graph and see what this looks like. See if it makes sense. So here's the graph from our calculator. So this blue curve right here is the 150 plus 250 times e to the negative, well, the calculator says x over 50. And let's just kind of double check that the y-intercept kind of makes sense right here. So if we plug in 0 in for t, then 0 divided by 50, this would just go away. You get 150 plus 250, which is 400. Does it make sense that the amount of blackness at the time of the start is 400? Well, let's think about it. What do we know about the blackness level? So we know that we started with a tank of 500, and it was, I wrote 40. I meant to actually say 80% black. That was my bad. Just ignore that typo. So 80% times 500 is in fact 400, so forget the fact that this is 200. That should just say 400 there. So that is actually the correct y-intercept. Now what's going on with this curve? Well, the amount of blackness is going down. It's getting diluted more and more by the gray mixture, the 30% that's being mixed in. And notice it's getting closer and closer to this 150 level right here. Well, why is it getting closer and closer to 150? Well, remember, 150 out of 500 is 30%. So it's getting more and more and more like 30%. Now, don't forget what the question asks. It says, how long does it take before you reach 40%? So this is why I actually did this calculation, because if we want to reach 40%, that means 40% times 500 is 200. So that means we want to have an amount of blackness. Our capital A is going to be 200, and we want to know what is the time going to be for that. So we just go to our equation here. So our equation is 150 plus 250 e to the, we don't know what t is yet, negative t divided by 50. That has to come out to be 200. Well, how do we solve for that? Well, just basic algebra at this point. Subtract the 150 over. So when you do that, The 150 goes away, and you're just left with 50 over there. Then we have to divide by the 250. So that's going to leave 1/5 on this side. Now how do we get rid of this e? Well, we basically have to take natural logs. So if you take natural logs, you get negative t over 50, because that was our exponent, is equal to the natural log of 1/5. Now to solve for t, we just have to multiply the negative 50 over. So we get the t is equal to the natural log of, and just to simplify things, instead of writing 1/5, I'm going to write it as 5 to the negative 1 power, because that's the same thing as 1/5. And why did I do that? Just for a little bit of simplification. You don't have to do this, but remember the easiest falling off a log, that log property is that if you're an exponent here, you roll over the log, the minus goes out, so that's just going to cancel that one. So at this stage, we're ready to just pull out the handy-dandy calculator. 50 times the natural log of 5, according to my calculator, is 80.472. Don't forget the units here are minutes. And the question says, how long did it take? This is an okay answer, but since the question asks for time, you want to answer in a complete sentence, and usually convert this to more sort of standard English for times. So the way you would say this is that it takes 1 hour, 20 minutes, and 23 seconds for the tub to reach a 40% grayness level. And I just computed that. I just knew that 60 minutes were an hour, which leaves 20 minutes, and then I multiplied the 0.472 by 60 to get the number of seconds. So that's it. That's our final answer. So just to kind of recap, is we did a change in minus change out and got a separable differential equation. We solved the differential equation with a particular solution using the initial condition, and then we plugged in to find the answer we want. So notice that this sort of goes through different steps, right? First you figure out the c using the initial condition, and then at the very end, once you actually have the formula with the c, then you finally plug in the fact that we want it to be 200 units of blackness and figure out the time. Sometimes people try to do this too early. But in the end, we did figure out how long it takes for that 500 gallons that started at 80% grayness to reduce to a 40% grayness when we're pouring in 30% grayness at 10 gallons per minute.